Earth became an enemy long before anything struck it from space. The first clue is preserved inside a strip of rock only a few centimeters thick. In southern China, at a place called Meishan, layers of pale limestone rise through the quarry wall, like the pages of an enormous archive. Lower down, those pages are crowded with shells, brachiopods, corals, tiny marine organisms whose skeletons accumulated for millions of years while the planet's oceans quietly recycled carbon and supported one of the richest ecosystems Earth had ever produced. Nothing about this boundary looks like the dramatic aftermath of a single explosive catastrophe. There is no continent-sized field of shattered rock, no unmistakable impact layer stretching across the outcrop. Instead, the transition is almost restrained. The greatest biological disaster in Earth's history announces itself through a subtle change in sediment. That quietness is exactly what makes the boundary so unsettling. For decades, the rock at this site became one of the most closely examined geological records on Earth. Every layer was measured, every fossil was cataloged, every grain of volcanic ash was sampled. Scientists were no longer looking only for destruction. They were looking for sequence. Because sequence reveals process. High-precision dating of volcanic ash fixed the main extinction pulse within an extraordinarily narrow geological interval. Not a single instant. Not an overnight catastrophe. But only about 60,000 years. On Earth's timescale, that is astonishingly brief. Entire marine ecosystems disappeared within that window. More than 90% of marine species vanished from the fossil record. The rocks record not only their disappearance, but the failure of complex ecosystems to return in the layers immediately above. The evidence refuses to behave like the end of a single event. It behaves like the beginning of something larger. Another clue appears beside the missing fossils. The chemistry of the rocks changes at exactly the same boundary. Carbon isotope records shift sharply across marine sections separated by thousands of kilometers. Independent geological sites preserve the same chemical disturbance alongside the same biological collapse. A local disaster cannot leave identical fingerprints across distant oceans. The investigation changes here. The fossils are no longer the only evidence. Earth's own chemistry has entered the case. The rock wall that first looked like a simple extinction layer has become something very different. It is a ledger recording the moment a stable planetary system began to fail. And whatever caused that failure reached far beyond the place where these rocks were formed. The first suspect seems obvious. A volcanic province in what is now Siberia erupted on a scale unlike almost anything else in Earth's history. Layer upon layer of basalt spread across the landscape, eventually covering an area measured in millions of square kilometers. At first glance, the explanation appears complete. A volcanic system this large must have overwhelmed the planet through sheer destruction. That expectation fits the landscape. It does not fit the evidence. The lava fields remained regional. The extinction did not. The disappearance of marine life is recorded in rocks deposited thousands of kilometers from Siberia. The same chemical disruption appears in distant seas. Whatever carried the catastrophe around the world traveled far beyond the reach of flowing basalt. The investigation moves underground. Beneath the ancient surface lay thick layers of coal, oil-bearing shale, and sulfur-rich evaporite deposits. As magma forced its way upward, much of it never reached open air. Instead, it spread sideways through these buried sediments, forming enormous sheets of molten rock known as sills. The important eruption was no longer the one anyone could see. It was the one happening inside the crust. Imagine a furnace inserted into vast underground stores of carbon and sulfur. As the magma heated these rocks, they did not simply crack apart. They underwent intense contact metamorphism. Coal, Organic-rich shale and ancient evaporite beds were baked at extreme temperatures, releasing enormous quantities of carbon dioxide, methane, sulfur dioxide, and halogen-bearing gases. The volcanic system had changed its role. It was no longer only producing lava. It was converting Earth's own buried carbon reservoirs into atmospheric gases. That idea would be difficult to accept if it existed only in computer models. It does not. Drill cores recovered from the Tunguska Basin preserved the altered contact zones where molten rock invaded carbon-rich sediments. Field exposures reveal the same relationships in exposed sill complexes. Scattered across the basin are pipe-like explosion structures formed as expanding gases force their way toward the surface. These are physical remnants of underground pressure escaping through the crust. Each piece of evidence changes the investigation. The lava confirms the eruptions. The altered sediments reveal what the eruptions were heating. The explosion pipes reveal where those newly formed gases escaped. Together, they reconstruct a volcanic system unlike the familiar image of mountains pouring rivers of molten rock across the landscape. Most of the planet-changing work happened where no one would have seen it. Far below the surface, the visible volcano becomes almost secondary. Its buried plumbing system becomes the true engine. The familiar picture of volcanic destruction no longer survives the evidence. The Siberian eruptions did not threaten the world because they covered enough ground with lava. They threatened the world because they transformed underground rock into an immense and persistent source of greenhouse and chemically reactive gases, feeding them into the atmosphere over thousands of years. The case has changed again. The volcano is no longer the destination of the investigation. It is the beginning of it. The gases released in Siberia did not remain over Siberia. They entered the atmosphere. At first, that seems almost ordinary. Volcanoes release gases. Greenhouse gases trap heat. The result appears straightforward. A warmer world. But the rocks preserve something far more consequential than a warmer climate. Across marine sections, separated by entire continents, carbon isotope records shift together. Independent formations in South China, Iran, Italy, and other Permian-Triassic boundary sites all record the same abrupt disturbance in the global carbon cycle. These were isolated seas with different local histories. Yet they responded as though they were connected. The atmosphere had become that connection. It was no longer simply the layer of air surrounding Earth. It had become the mechanism carrying instability around the planet. That changes the investigation completely. If the atmosphere was transporting vast quantities of newly released carbon, then the extinction could no longer be explained by regional volcanic destruction. Something much larger had begun. The planet's entire energy balance was changing. Climate evidence preserved in the geological record points to a world that warmed by roughly 10 degrees Celsius. That number is difficult to picture. The difference between the modern world and the last ice age was only a few degrees spread across the globe. Here, the increase was roughly twice that magnitude. Enough to reorganize climate on a planetary scale. The atmosphere was no longer buffering Earth's surface. It was trapping more and more of the sun's energy. Heat accumulated year after year, century after century. The process did not depend on a single eruption. It depended on greenhouse gases entering the atmosphere faster than Earth's natural systems could remove them. The familiar image of a volcano begins to fade. In its place is something much harder to see. An increasingly carbon-rich atmosphere wrapped around the entire planet. The evidence no longer describes a series of isolated disasters. It describes one expanding system. Every additional pulse of carbon strengthened the greenhouse effect. Every increase in trapped heat altered the exchange of energy between the atmosphere and the oceans. The air was no longer acting only as Earth's protective envelope. It had become a transmission system. What began beneath the Siberian crust was now being delivered to every ocean basin on Earth. The investigation reaches another irreversible point. The original assumption was simple. Volcanoes destroyed the world because they erupted. The geological record now supports a different picture. The eruptions mattered because they transformed the chemistry of the atmosphere. Once that transformation occurred, the disaster no longer belonged to Siberia. It belonged to the planet. But the atmosphere was only carrying the crisis. The largest consequences were still waiting below the surface of the oceans. The oceans absorbed much of the heat. For a time, they still looked familiar. From above, Earth remained a blue planet. The evidence hidden inside the rocks tells a very different story. Some of the smallest fossils ever recovered from the Permian-Triassic boundary became the next witnesses in the investigation. They belonged to conodonts, eel-like marine animals whose tiny tooth-like elements preserved the chemistry of the seawater in which they lived. Those microscopic fossils became ancient thermometers. When researchers measured the oxygen isotopes locked inside exceptionally well-preserved conodont elements, the numbers pointed to an extraordinary result. Equatorial sea surface temperatures climbed from roughly 21 degrees Celsius to nearly 40 degrees. Water approaching the temperature of a modern hot tub had become part of the tropical ocean. Heat alone seems sufficient to explain a catastrophe. It is not. Warm water changes more than comfort. It changes chemistry. As the oceans heated, they became less capable of holding dissolved oxygen. The great circulation systems that normally carried oxygen-rich surface water into deeper basins weakened. Large regions of the ocean began losing one of the ingredients that complex marine life depended upon most. The first measurements of temperature opened a new question. The next measurements answered it. Boron isotopes preserved in marine carbonates recorded a rapid fall in ocean pH. During the main extinction interval, surface seawater became dramatically more acidic, dropping by roughly 6 to 7/10 of a pH unit. That is not a cosmetic change. It alters the chemistry countless organisms use to build shells and skeletons from dissolved carbonate. The investigation changes again. The oceans were not simply becoming hotter. The water itself had changed. Yet even that was not enough to account for the scale of extinction. Another line of evidence refused to fit a warming-only explanation. Uranium isotopes preserved in boundary sediments showed that oxygen depletion was spreading across marine environments. Entire regions of the seafloor were becoming anoxic, almost devoid of the oxygen required by most complex animals. One final discovery pushed the reconstruction beyond anything visible from the surface. Organic molecules preserved in the rocks revealed the former presence of green sulfur bacteria. These microorganisms survive only under very specific conditions. They require sunlight. They also require water-rich and toxic hydrogen sulfide and almost completely lacking oxygen. Finding their chemical fingerprints at the extinction boundary means something remarkable had happened. Hydrogen sulfide-rich water had risen out of the deep ocean and invaded the sunlit surface, where most marine ecosystems had once flourished. The shallow seas themselves had become chemically hostile to complex life. The blue planet returns. Nothing about its appearance has changed. Its oceans still cover most of its surface. But the investigation has transformed what that blue now means. The water is hotter. It is more acidic. It carries less oxygen. In many regions, toxic chemistry has reached places that had supported thriving marine ecosystems for millions of years. The extinction was no longer best explained by volcanic eruptions, nor by heat alone. The strongest explanation now lies in a chain of chemical failures that turned Earth's largest habitat into its most efficient extinction mechanism. The oceans had become the engine of the Great Dying. The collapse did not stop at the shoreline. For a long time, it was tempting to imagine two separate disasters. One in the oceans, another on land. The geological record does not preserve that separation. As marine ecosystems unraveled, the continents were changing as well. The evidence appears in places that had once been covered by vast forests. Late Permian landscapes supported extensive communities of Glossopteris and other plants that stabilized soils, recycled nutrients, and formed the foundation of terrestrial food webs. In younger rocks above the extinction boundary, those familiar assemblages become scarce or disappear altogether. The forests were no longer performing the same role. That conclusion does not come from trees alone. Microscopic grains preserved in sediment reveal sudden increases in fungal and microbial material. These unusual spikes appear alongside signs of widespread soil erosion, suggesting landscapes where stable vegetation had broken down and exposed the ground to weathering. The investigation changes once more. The oceans had already been shown to fail through heat, acidification, and oxygen loss. Now the land begins to display its own symptoms. Without extensive plant cover, soils that had accumulated over immense spans of time became vulnerable. Rivers carried increasing amounts of sediment into lakes and shallow seas. Habitats that had once supported diverse communities became simpler and less stable. The evidence does not point toward isolated ecological accidents. It points toward one connected environmental system responding to the same planetary disturbance. Fossil records reinforce that picture. Many groups of terrestrial vertebrates declined sharply across the same interval that marine communities collapse. Plant communities reorganize. Animal communities simplify. Organisms that had flourished for millions of years vanish from successive layers of rock, replaced by a much smaller collection of survivors. The expectation that land might have provided refuge becomes increasingly difficult to defend. The atmosphere surrounded both continents and oceans. Changes in atmospheric chemistry influenced climate everywhere. The oceans redistributed heat across the globe. Vegetation responded to altered temperatures and environmental stress. Soils deteriorated. Food webs fractured. Each system amplified pressure on the next. The evidence no longer supports separate stories unfolding in parallel. It supports a single chain reaction spreading through every major environment on Earth. A global map of extinction sites makes that pattern unmistakable. Marine boundary sections preserve the disappearance of reef builders, brachiopods, crinoids, and countless other organisms. Continental deposits record collapsing forests, changing pollen assemblages, soil instability, and heavy losses among terrestrial vertebrates. These records come from different continents, different climates, and different depositional environments. Yet they converge on the same conclusion. No major ecosystem remained isolated from the failure of Earth's life support systems. Earth returns once again. Its continents still exist. Its oceans still surround them. Its atmosphere still encircles both. Physically, the planet looks familiar. Functionally, it has become something else. The investigation no longer follows separate environmental crises. It now describes a single planetary system in which failure in one component propagated into every other. By this stage of the Great Dying, there were no unaffected worlds left on Earth. only different expressions of the same collapse. The main pulse of extinction eventually passed. The rock record makes that clear. What it does not show is a rapid return to the world that existed before. At first, that seems surprising. If the most intense volcanic activity declined, if the great wave of biological loss had already swept across the planet, then recovery should have followed. Instead, the rocks preserve a different reality. Layer after layer of early Triassic sediment records ecosystems that remained remarkably simple. The extraordinary diversity that filled late Permian seas does not suddenly reappear. Reef systems remain rare. Complex marine communities struggle to reestablish themselves. Across both marine and terrestrial environments, low-diversity survivor communities dominate the landscape for an immense span of geological time. The investigation changes one final time. The extinction itself was no longer the only event requiring explanation. Recovery had become part of the mystery. If life had survived, what was preventing the planet from rebuilding? The answer is written into the chemistry of the younger rocks. Carbon isotope records continue to fluctuate throughout the early Triassic. Instead of settling into a stable pattern, the carbon cycle experiences repeated disturbances, suggesting that Earth's environmental systems remained unstable long after the greatest pulse of extinction had ended. The atmosphere was still changing. The oceans were still responding. The planet had survived. Its life support systems had not yet recovered. The fossil record tells the same story from another direction. Many surviving organisms became noticeably smaller than their predecessors. Paleontologists call this the Lilliput effect, a recurring pattern seen after severe environmental crises. Reduced body size appears across multiple marine groups, reflecting ecosystems operating under persistent stress rather than renewed stability. The world was inhabited. It was not yet healthy. Millions of years pass through successive layers of sediment. Only gradually does biodiversity begin to increase again. Complex ecological relationships slowly return. New communities form where older ones had vanished forever. The rebuilding is measurable, but it unfolds over 5 to 10 million years. Not generations, not centuries. Millions of years. Earth returns one last time. The same planet that opened this investigation. The same continents. The same oceans. The same atmosphere. But now the rock record carries a different meaning. The fossil-rich limestones below the boundary no longer represent an ordinary ancient sea. The ash layer is no longer just a thin interruption in sediment. The barren strata above are no longer simply rocks with fewer fossils. Together, they preserve the complete history of a planetary life support system pushed beyond its operating limits. The atmosphere accumulated carbon faster than natural processes could restore balance. The oceans absorbed the consequences. Their chemistry changed. Marine ecosystems collapsed. The disturbance spread across forests, soils, rivers, and continents. Recovery began only after millions of years of rebuilding, recorded one layer at a time in Earth's stratigraphic archive. The investigation ends where it began, at a quiet boundary in stone. Nothing about the outcrop appears dramatic. Yet within a few centimeters of rock lies the documented record of the greatest biological collapse in Earth's history, followed by the slow reconstruction of a living planet. The rocks remain unchanged. Our understanding of them does not.